If you are wearing any gold jewelry right now, maybe a wedding band, a necklace, or even if you're just holding the smartphone that's sitting in your pocket right now, I want you to take a moment and really look at it and just pause and consider that physical material.
Yeah, we tend to view it purely as a symbol of human wealth or status. You think of it sitting in a bank vault or in a jewelry store window.
Right, exactly. But the actual story of that metal, it is so much bigger, so much older, and honestly, so much stranger than anything you could possibly imagine. Welcome to today's deep dive. We have an absolutely massive stack of material in front of us today, and our mission is to take you on a comprehensive exploration of the single extraordinary element.
And this isn't just some dry history lesson about ancient coins. We're going to be connecting the dots across astrophysics, human biology, the cutting-edge technology of the AI revolution, and the foundational economic systems that have literally shaped the modern world.
Okay, let's unpack this.
It really is a phenomenal journey. To truly understand gold, you have to realize that it bridges the gap between the infinitely large and the microscopically small.
Yeah.
Our goal today is to synthesize all of this diverse information from the sources to show you the complete picture. We're looking at how this material is forged in the most extreme environments in the universe, how its unique atomic structure makes it behave unlike almost any other element, how it interacts or completely fails to interact with the human body.
Which is wild, by the way.
Right. And why it has quietly become the unsung backbone of our modern electronic age. And of course, we have to examine the profound psychological and economic hold it has over human civilization. But to do that, we have to start at the very beginning. And by the beginning, I mean the violently energetic origins of the universe itself.
That is the perfect place to start because this is a point that completely blew my mind when I was reviewing the astronomy research for this deep dive. Gold is not made on Earth, not a single ounce of it.
No.
Every piece of gold you have ever touched, seen, or interacted with was forged in deep space, and not just anywhere in space. For a very long time, the origin story of gold was actually a massive, glaring mystery for astrophysicists. We knew that the Big Bang basically only gave us the lightest elements, right? It gave us a universe filled with hydrogen and some helium.
Precisely. And from there, the universe had to essentially build the rest of the periodic table. We know that normal stars, like our sun, act as giant cosmic furnaces. They are powered by nuclear fusion.
Right.
The intense gravity of the star crushes hydrogen atoms together to form helium, and this process releases the energy that makes the star shine. As stars age and exhaust their hydrogen, they start fusing heavier and heavier elements. They fuse helium into carbon, carbon into oxygen, building up the elements that are essential for life.
Up to a point.
Exactly. In their dying phases, massive stars can continue this fusion chain all the way up to common metals like aluminum and iron.
But that's exactly where the stellar assembly line it breaks down. The fusion process in a normal star hits an absolute brick wall at iron. Fusing elements lighter than iron releases energy, which holds the star up against its own gravity. But fusing iron actually requires more energy than it produces. It's an energy sink.
The star suddenly loses its outward pressure. Gravity takes over instantly, and the core collapses. So for decades, scientists were scratching their heads. If a star's internal furnace shuts down at iron, where on Earth, or rather, where in the universe, did the heavy, incredibly dense elements like gold actually come from?
And for a long time, they thought they had the answer with supernovae, right?
They did. The prevailing theory was that the explosive deaths of these massive stars, the supernovae, were responsible. The thinking was that when a massive star collapses and rebounds in a supernova explosion, the sheer kinetic force and the extreme temperatures of a star tearing itself apart might provide that sudden burst of necessary energy to force fusion past iron.
It makes intuitive sense. You need extreme energy to make heavy elements, and a supernova is one of the most energetic events we know of.
Right. But as astrophysics advanced and our mathematical models became much more rigorous, a glaring problem emerged.
The math just didn't add up, did it?
It really didn't. When physicists modeled the nuclear reactions inside a supernova, they realized that while some heavy elements could be created, supernovae alone simply couldn't account for the sheer abundance of heavy elements we actually observe in the universe, particularly when looking at very old stars.
The timeline and the volume were just wrong.
Exactly. The universe needed a crucible even more extreme, more dense, and more exotic than a standard supernova. It required an environment that could trigger a very specific, highly theoretical nuclear reaction known as the R process.
The R process. Yes, this is where the physics gets incredibly dramatic. The R stands for rapid. the rapid neutron capture process. Because to make gold, which is element 79, you need an environment with a staggering density of free-floating neutrons, and you need temperatures that make a supernova look like a matchstick.
And scientists theorized about this for a long time, but they finally witnessed this exact, supposedly impossible environment on a very specific date.
I love this part.
Picture this. It's the morning of August 17th, 2017. A literal ripple in the fabric of space-time washes over our planet.
This is one of the most significant moments in modern astronomy. This cosmic disturbance, this gravitational wave, was detected by the LIGO and Virgo observatories. They cataloged the event as GW 170817. Gravitational waves are essentially stretching and squeezing the very fabric of reality as they pass through. To create a ripple that we can detect from Earth, you need an event of unimaginable violence involving incredibly massive, dense objects.
And what caused this specific ripple? It was a pair of city-sized neutron stars colliding at one-third the speed of light.
Let's just pause on that for a second. Two objects the size of a city smashing into each other at a fraction of the speed of light.
What's fascinating here is the sheer scale of the physics involved. To truly grasp what collided that day, you have to understand the nature of a neutron star. When that massive star we talked about earlier dies and goes supernova, it blows off its outer layers, but it leaves behind a core. If that core is massive enough, gravity continues to crush it inward until the very atoms themselves collapse.
The empty space in the atom is just gone.
Completely. The electrons are smashed into the protons, creating a solid sphere of almost pure neutrons. A typical neutron star packs roughly 1.5 times the entire mass of our sun into a sphere that is only about 10 miles across. It is matter compressed to the absolute breaking point of physical laws.
I found an analogy in the research that puts that density into perspective, and it is honestly terrifying. If you were to take just a single teaspoon of material from the surface of a neutron star, that tiny amount of matter would weigh 10 million tons.
It's hard to even picture.
Imagine trying to hold a teaspoon that weighs as much as thousands of fully loaded freight trains. That is the density we are dealing with. And in this particular binary system, these two unbelievably dense 10-mile-wide objects had been locked in a gravitational dance, orbiting each other for hundreds of millions of years. But exactly as Einstein's theories of general relativity predicted, that dance was decaying.
They were bleeding off energy in the form of gravitational waves.
Right. Spiraling inward, closer and closer, faster and faster, until they finally smashed into each other.
And that collision produced an energy release that surpasses any atom-smashing laboratory we could ever conceive of building on Earth. The moment that collision happened, astronomers around the world basically dropped everything they were doing. About 12 hours after the gravitational waves hit Earth, 3 different optical telescopes caught sight of a brand new, incredibly bright object in the sky, a phenomenon we call a kilonova.
In a galaxy called NGC 4993.
Which sits about 130 million light years away from us. Which means the cosmic fire we were seeing, the actual collision, burned 130 million years ago, right around the time dinosaurs were walking the Earth. And the light was just arriving in our telescopes in 2017. The scramble to observe this was unprecedented. You had the Gemini telescope in Chile frantically swerving its massive 26-foot mirror to catch the fading light of this kilonova. NASA steered the Hubble Space Telescope to look at the exact same coordinates.
And what they were looking for wasn't just a bright flash. The secret was encoded in the light itself.
In the spectrum.
Exactly. Just as a glass prism splits sunlight into a rainbow of colors, astronomers use spectrometers to split the light from these distant cosmic events. Because of quantum mechanics, every single element in the universe absorbs and emits light at very specific, unique wavelengths. It leaves a fingerprint.
A specific pattern of dark and bright lines.
Yes, based on its atomic structure. And when the teams analyzed the visible and infrared spectrum of this kilonova as it faded over the following days and weeks, they saw something revolutionary. They found the fingerprints. The light carried the unmistakable telltale signature of massive amounts of neutron star material decaying into heavy elements, specifically platinum and, yes, gold.
This was the smoking gun for the rapid neutron capture process. The Rohr process was happening right before our eyes. In the chaotic, ultra-dense debris cloud ejected by that collision, the density of free neutrons was so extreme that existing iron nuclei were bombarded with them. The nuclei captured neutron after neutron so rapidly that they didn't even have time to undergo radioactive decay before capturing the next one.
It just rapidly bulked up,
Transforming in fractions of a second into the heaviest elements in the universe, including element 79. For the first time in human history, we had directly observationally confirmed the site of cosmic alchemy. We watched the universe turning raw, hyperdense matter into gold.
And the sheer volume of it. It's not like they created a couple gold bars out there. The estimates from analyzing that light spectrum suggest that this single collision, that one split-second event, produced an amount of pure gold estimated to be between 3 and 13 times the mass of the entire Earth.
It is staggering to conceptualize.
Hmm.
3 to 13 entire planets worth of solid gold, forged in an instant and blasted out into the interstellar medium at immense speeds.
And over billions of years, that gold dust drifts through space. It mixes with giant clouds of hydrogen gas and other stellar debris. Eventually, gravity pulls those clouds together to form new star systems, new protoplanetary disks, and eventually, new planets, like ours. Which brings us right back to you, the listener. That gold tracing the microscopic circuits in your phone, or the gold ring you might be wearing. It was literally forged in the cosmic fire of two dead, hyperdense stars smashing into each other at a third of the speed of light. It is, quite literally, ancient stardust.
This raises an important question, though, regarding how that gold actually ended up in our hands. You might assume that when the Earth formed from that swirling disk of stardust, the gold was just mixed into the rocks we walk on today. But gold is incredibly dense. During the very early stages of Earth's formation, the planet was essentially a molten ball of magma. Because of its extreme density, almost all of the gold that was originally present in the Earth's crust sank straight down, migrating thousands of miles deep into the planet's molten iron core.
Right. The amount of precious metals locked in the Earth's core is theoretically enough to cover the entire surface of the planet in a layer several feet thick, but it's totally inaccessible to us.
Exactly. So, if all the original gold sank to the core, why is there any gold in the crust for us to mine today? The prevailing geological evidence indicates that the gold we actually mine, the gold we use in our jewelry and technology, arrived much later. Long after the Earth's crust had cooled and solidified, the planet was subjected to a period known as the Late Heavy Bombardment.
A barrage of asteroids.
Massive meteorites, which also contain gold forged in kilonovae, pummeled the surface of the Earth. These impacts essentially sprinkled a fresh layer of gold and other precious metals onto the solidified crust. It's a veneer of cosmic debris that we've been scraping away at for millennia.
So not only was it forged in a cosmic collision, but it was also delivered to us by an asteroid bombardment. It's just a spectacular, violent origin story. But before we move on to what gold actually looks and feels like, I want to touch on one more recent astronomical discovery from our notes that refines this origin story even further.
Yes, the timeline issue.
Whoa.
While neutron star collisions are undeniably prolific gold factories, they are relatively rare events. In a typical galaxy like our Milky Way, a merger like the one we saw in 2017 might only happen once every 100,000 years. Furthermore, they tend to happen much later in a galaxy's timeline. It takes millions of years for massive stars to live out their lives, die in supernovae, become neutron stars, and then hundreds of millions or billions of years for their orbits to decay until they collide.
Right, so if you look at the oldest, most ancient stars in the universe, stars that formed very shortly after the Big Bang, they shouldn't have any gold in them at all, because there hadn't been enough time for neutron stars to form and collide. But astronomers looked, and they did find traces of gold in those ancient stars. The timeline was completely broken.
And this is where recent research into magnetars provides a brilliant solution. A magnetar is a specific, highly magnetic type of neutron star. They possess magnetic fields quadrillions of times stronger than Earth's. And scientists have now found strong evidence that giant flares from these magnetars can also trigger the R process. Think of them like solar flares from our sun, but on a terrifyingly massive energetic scale.
So the magnetic field gets twisted up and suddenly snaps, releasing a massive burst of energy and particles.
Precisely. And in that burst, the conditions are just right for rapid neutron capture. The key here is that magnetar flares happen much earlier in a star system's history and occur far more frequently than full-on binary neutron star collisions. The current estimates suggest that these flares might be responsible for producing between 1 and 10% of all the heavy elements in the Milky Way. This beautifully resolves the timeline paradox. It explains how gold was being synthesized and sprinkled across the galaxy even in its infancy, seeding those very early ancient stars.
I love how the universe has multiple different extreme factories just to make this one element, but let's bring that gold down to Earth and look at what it actually is in our hands. Because once you get past the astrophysics, the physical wonders and the chemical quirks of this metal are just bizarre. Let's talk about the element itself. The chemical symbol for gold is O.
That comes from the Latin word aurum, which poetically translates to shining dawn.
And the English word gold comes from the Old English word giolu, meaning yellow, which itself derives from the ancient Germanic word gula. So from the very beginning of human language, we've been naming this thing after its defining visual characteristic, its color and its shine.
Chemically, it is classified as a transition metal. It sits in group 11 of the periodic table, holding the atomic number 79. But what makes gold truly stand out in the physical world is its seemingly contradictory nature. It is defined by a combination of extreme density and extreme softness. As we mentioned with the Earth's core, it is incredibly dense. To visualize this, a single cubic foot of gold, a block that could easily sit on your lap, weighs over 1,200 pounds. It's nearly twice as dense as lead.
Yet, despite being so unimaginably heavy, it is the most malleable and ductile metal known to humanity. The malleability is just insane. A skilled goldsmith can take a single ounce of pure gold, which is a physical piece roughly the size of a modern quarter, and they can hammer it out into a continuous, unbroken sheet of gold leaf that covers 300 square feet. You could essentially wallpaper an entire small bedroom with one single ounce of gold. It just keeps stretching without fracturing.
And its ductility is equally impressive. Ductility is a material's ability to be drawn out into a wire. You can take that exact same 1 ounce nugget of gold and pull it into a wire that stretches for over 50 miles without it snapping.
50 miles from one coin-sized piece.
In laboratory settings, scientists have actually pulled gold into a monatomic wire, a wire that is literally just one single atom thick, and it maintains its structural integrity. This supreme physical flexibility is a major reason why ancient human civilizations, who didn't have access to modern blast furnaces or complex industrial machinery, were able to work with it so easily for thousands of years. It can be shaped with nothing more than basic tools and heat.
But there is another very obvious physical trait we have to talk about. Most metals, when you think about them, iron, aluminum, silver, platinum, titanium, they're all basically variations of silvery gray. Gold is distinctly, vividly yellow. Why is it the odd one out?
What's fascinating here is that the answer lies in relativistic quantum chemistry.
That sounds incredibly complicated.
It sounds intimidating, but it's fundamentally about speed. The yellow color of gold is a direct result of how its electrons behave, specifically due to the effects of Einstein's theory of special relativity operating within the atom itself. Because the nucleus of a gold atom has 79 protons, it exerts a massive positive charge. The negatively charged electrons orbiting close to this heavy nucleus have to move incredibly fast to avoid being pulled into the light. They're traveling at a significant fraction of the speed of light.
So relativity actually kicks in inside the atom.
Exactly. At those relativistic speeds, the mass of the electrons effectively increases, which causes their orbitals to contract and shift closer to the nucleus. This slight shift changes the amount of energy required for an electron to jump between energy levels.
Okay, so how does that affect the color?
Well, for most metals, this energy gap corresponds to the ultraviolet spectrum, meaning they reflect all visible light, which our eyes perceive as silvery white. But for gold, the relativistic contraction narrows that energy gap. It shifts the absorption spectrum down into the visible range, specifically into the blue and violet light frequencies. So when white light hits a piece of gold, the gold atoms absorb the blue light, and they reflect the rest of the spectrum, the reds, oranges, and yellows. That selective reflection is what gives gold its distinct, warm, yellow glow.
That is incredible. The color we have obsessed over for millennia is essentially a quantum optical illusion caused by electrons moving at near light speed. And practically speaking, the only other solid elemental metal we use in daily life that has a distinctly non-gray color is copper, which is reddish.
Yes. There is cesium, which also has a somewhat gold-like yellowish color, but cesium is a highly reactive alkali metal. If you expose cesium to air, it ignites. You drop it in water, it explodes violently. It is not something you can wear on your finger. Gold, on the other hand, is the exact opposite of reactive. It is classified as a noble metal.
A noble metal, meaning it is highly aloof. It basically ignores the rest of the chemical world. It does not tarnish, it does not rust, it does not oxidize. You can take a pure gold coin, drop it into the bottom of a corrosive, salty ocean, leave it there for 1,000 years, and when a diver pulls it up, it will still be shining exactly as it did the day it was minted. It simply refuses to bond with oxygen or sulfur the way iron or silver does.
This chemical aloofness, this absolute resistance to corrosion, is precisely why it has been so valued as a store of wealth. It represents permanence in a world where almost everything else degrades. But it is not entirely invincible. While it ignores the oxygen in the air and the salt in the sea, there are very specific, almost bizarre ways you can force gold into a chemical reaction. For instance, it is completely immune to most normal acids. You could drop gold in sulfuric acid or nitric acid, and nothing would happen.
Yeah.
But early chemists and ancient alchemists discovered a very specific concoction that could defeat it.
Yes, a mixture called aqua regia, which translates from Latin to royal water. It's called royal water because it can dissolve the royal metal. It is a highly corrosive, fuming, yellow-orange mixture of nitric acid and hydrochloric acid. And what's wild is that neither of those acids can dissolve gold on their own. If you put gold in pure nitric acid, it just sits there. If you put it in pure hydrochloric acid, it just sits there. But you mix them together, and suddenly the gold starts foaming and disappearing.
It's a fascinating chemical synergy. Nitric acid is a powerful oxidizer, but its reaction with gold is so incredibly slow, it's virtually imperceptible. However, when you introduce the hydrochloric acid, you introduce an abundance of chloride ions. So the nitric acid acts as the oxidizer, prying a tiny fraction of gold ions loose from the solid metal. Immediately, the chloride ions from the hydrochloric acid react with those gold ions to form a stable compound called tetrachloroate. By constantly pulling the gold ions out of the reaction, the chloride allows the nitric acid to keep attacking the metal, slowly but surely eating away the entire piece.
And this interaction is actually the origin of the phrase, the acid test. Because nitric acid by itself leaves pure gold completely untouched, but it rapidly dissolves lesser metals like silver, copper, or lead. Ancient merchants and early bankers would literally use a drop of nitric acid to test whether someone was trying to pass off fake gold or an alloy that was heavily diluted with cheap metals. If the acid burned it or turned green, the person was lying. It wasn't pure gold. That literal physical chemical test gave us the metaphorical phrase we use today for any definitive test of truth or authenticity.
Beyond aqua regia, there are a few other substances that can overcome gold's nobility. Cyanide solutions, specifically highly alkaline cyanide, can dissolve gold. This is actually a property heavily utilized in modern industrial mining. They crush gold-bearing ore into fine dust and wash it with a weak cyanide solution, which leaches the microscopic gold particles out of the rock so they can be recovered later. It's efficient, but highly toxic. Gold also interacts quite dramatically with mercury.
Right, forms an amalgam. Though, from what I read in the chemistry notes, when gold interacts with mercury, it isn't really chemically reacting in the traditional sense of forming new molecular bonds.
That's correct. It's more akin to a physical mixing process, much like how sugar dissolves in warm water. The gold atoms diffuse into the liquid mercury, creating an alloy called an amalgam. This property has also been used extensively throughout history for mining and purification. Miners would use liquid mercury to capture fine gold dust from river sediment. The gold would dissolve into the mercury, forming a heavy, silvery lump. Then they would take that lump and heat it. The mercury, having a much lower boiling point, would vaporize into a highly toxic gas, leaving the pure sponge gold behind.
It's horrifying to think about the neurological damage those early miners suffered breathing in vaporized mercury just to isolate some gold. Now, before we move away from the deep chemistry and physics and get into how gold interacts with the human body, we have to talk about its isotopes. Because the research dedicated to the atomic structure of gold provides some incredibly deep, almost philosophical context about its permanence. Gold is currently recognized as the heaviest monoisotopic element on the periodic table.
To put that into context, an isotope is simply a variant of a chemical element. Every single atom of gold in the universe always has exactly 79 protons in its nucleus. That is what makes it gold. But atoms can have varying numbers of neutrons. These variations are called isotopes. Most elements in the periodic table have multiple stable isotopes, different configurations of neutrons that hold together perfectly fine. But gold is unique among the heavy elements. Element 79 has only one single stable isotope occurring in nature, gold-197. It has 79 protons and exactly 118 neutrons. Every single other isotope of gold is radioactive and inherently unstable.
And what's really interesting is that bismuth actually used to hold the title of the heaviest monoisotopic element. We always thought bismuth had one perfectly stable isotope. But then not too long ago, scientists ran some incredibly sensitive experiments and observed that bismuth's supposedly stable isotope actually undergoes alpha decay. It's radioactive, but its half-life is over 1 billion times longer than the estimated age of the universe. So bismuth lost the title, and gold-197 became the reigning heavyweight champion of stability.
But even gold-197 has a caveat attached to it in the realm of theoretical physics. It is currently classified as observationally stable.
Observationally stable, meaning we've never seen it decay, but the math says it might.
Exactly. According to the highly complex mathematical models of particle physics, gold-197 shouldn't actually be perfectly eternally stable. It is theoretically predicted to eventually undergo a process called alpha decay, where it spits out an alpha particle and transforms it to an isotope of iridium, specifically iridium-193. However, the predicted half-life for that decay event is so incomprehensibly, staggeringly long that in the entire 13.8 billion year history of the universe, no one has ever observed a single atom of gold-197 undergoing this decay. The probability is so low that, for all practical human purposes and probably for the lifespan of our solar system, it is functionally immortal.
It is an immortal atom. Now, scientists have played around and created radioactive isotopes of gold in the lab, right?
Yes. Through nuclear bombardment and particle accelerators, physicists have synthesized numerous radioactive, unstable variants of gold, ranging from gold-169, which is missing a ton of neutrons, all the way up to gold-210, which has way too many. These isotopes decay quickly. The most stable of these artificial radioactive variants is gold-195, which has a half-life of about 186 days before it captures an electron and decays into platinum. The heavier synthetic isotopes usually undergo beta decay, shooting out an electron to become an isotope of mercury. But it's crucial to understand that none of these radioactive variants exist naturally on Earth today. Any natural radioactive gold decayed away billions of years ago. If you're holding a piece of gold jewelry, you're holding 100% pure gold-197.
Which naturally leads us to wonder, what happens when we put this immortal, completely unreactive, monoisotopic metal inside mortal biological bodies? Because humanity has been obsessed with putting gold inside themselves for centuries. Let's look at the human body, medicine, and the wild myths surrounding gold. Let's start with the most basic interaction: eating it. What is the actual nutritional or biological value of eating pure 24-karat gold? Absolutely, scientifically, unequivocally zero.
That is correct. It provides no caloric value, no vitamins, no essential trace minerals. Because pure metallic gold is a noble metal and profoundly chemically inert, the human digestive system has absolutely no mechanism to break it down. Our stomach acid, hydrochloric acid, is strong, but as we discussed with aqua regia, it cannot dissolve gold on its own. So the gold does not react in the stomach, it does not get absorbed through the intestinal walls into the bloodstream, and it does not interact with our cellular biology. It simply passes through the entire gastrointestinal tract completely unchanged and is excreted.
Which makes the modern culinary trend of affluent people eating $100 donuts wrapped in gold leaf or massive steaks covered in gold foil completely ridiculous from a biological standpoint. It is purely an ego trip. You are paying for a visual flourish that provides zero flavor enhancement, zero texture improvement, and absolutely zero health benefits. You're just renting the gold for about 24 hours. And this isn't even a new modern fad. The source material mentions Danziger Goldwasser, which is a Polish vodka liqueur that has been produced in the city of Gdansk since 1598. It is literal, visible shreds of gold leaf floating right in the bottle. Wealthy European aristocrats have been drinking it for over 400 years, essentially showing off that they are so immensely rich they can afford to literally consume gold and flush it away. It's the ultimate flamboyant flex, but biologically it's a non-event.
While consuming pure gold leaf is biologically harmless, there's a very pervasive, deeply entrenched myth about gold interacting with human skin that the medical sources specifically address and debunk. And it stems almost entirely from pop culture, specifically the 1964 James Bond movie Goldfinger.
Oh, this is such a classic urban legend. In the movie, there's an iconic scene where the villain, Boric Goldfinger, kills a character named Jill Masterson, played by the actress Shirley Eaton, by painting her entire body in gold paint. And James Bond explains that she died of skin asphyxiation because humans supposedly breathe through their skin and the paint blocked her pores. The movie made it sound so scientific, and the urban legend spread rapidly outside the movie that the actual actress, Shirley Eaton, died on set from the exact same cause. People genuinely believed it for decades.
Which is entirely a biological impossibility. The premise is fundamentally flawed. Humans are mammals. We do not breathe through our skin like amphibians do. We respire exclusively through our noses, mouths, and the alveolar network in our lungs. Covering your body in an impermeable layer of paint will absolutely not cause you to suffocate from oxygen deprivation. The medical literature notes that Shirley Eaton was perfectly fine after filming that scene, and as of the latest checks, is alive and well. However, the source material does offer a crucial, very real medical caveat regarding full-body paint. While you won't suffocate, painting yourself head to toe is not entirely safe if you use the wrong materials.
Right. If you decide to cover yourself in standard, Polymerizing acrylic paints, the kind meant for painting a canvas or a house, rather than specifically formulated cosmetic skin paint, you can induce a severe medical emergency. But it's not asphyxiation, it's heat stroke. Your skin is your body's primary thermoregulation organ. We cool down by sweating. If you block all your sweat pores with industrial paint, you shut down the body's cooling system. Your core temperature will spike rapidly. Plus, those industrial paints contain toxic solvents, ammonia, and formaldehyde that can be absorbed transdermally and poison you. So the danger isn't the gold color, and it isn't suffocation. It's overheating and chemical toxicity.
Moving from cinematic myths to actual documented medicine, there is a legitimate medical application of gold that has been used for nearly a century, known as chrysotherapy or orotherapy. But this requires a fundamental chemical shift in how we approach the metal. As we firmly establish, pure metallic gold 197 is totally inert. If you swallow a gold coin, nothing happens. Therefore, to have any biological or pharmacological effect whatsoever, the gold must be chemically converted.
You have to strip away its nobility, basically.
Exactly. You have to react it with other chemicals to turn it into gold salts. This creates ionized gold compounds that can actually dissolve in bodily fluids and interact with cellular machinery.
And this is where the medical history gets really interesting. Since the 1930s, doctors have been using these ionized gold salts to treat rheumatoid arthritis. We are talking about highly specific manufactured compounds with names like SKF, 39162, Aranafin, and sodium orothiomylate. Now, rheumatoid arthritis is not just normal joint wear and tear. It is a devastating autoimmune disease where the body's immune system gets confused and actively attacks its own joints, causing severe, crippling pain, massive swelling, and eventual bone erosion. And for decades, before the invention of modern targeted therapies, injecting these heavy gold salts directly into a patient's muscles was one of the primary frontline ways to try and slow down the progression of the disease.
It was a blunt instrument, but often the best available. The precise, localized molecular biology of exactly why ionized gold works to calm the immune system is still somewhat obscure, even with modern research. However, we do know that these gold salts are classified as DMARDs, disease-modifying antirheumatic drugs. When the ionized gold enters the biological system, it accumulates in the tissue macrophages. It appears to modulate the immune system's hyperactive response, interfering with the inflammatory pathways, which significantly alleviates joint pain and acts prophylactically to prevent further structural degeneration of the joints. It actually works. But there is a profound, almost tragic irony inherent in chrysotherapy.
The irony is the toxicity. Pure elemental gold is one of the safest, most non-toxic, biocompatible elements you can possibly handle. But the moment you force it into a biologically active salt so it can treat a disease, it becomes highly toxic to the human body. The side effects of gold salt therapy are notoriously brutal. The medical journals and our sources note that it can cause thrombocytopenia, which is a dangerous drop in blood platelets, leading to bleeding issues. It frequently causes severe dermatitis, resulting in massive itching skin rashes. Patients often develop painful oral ulcerations throughout their mouth and throat. And most dangerously, it can cause significant irreversible kidney damage.
The therapeutic window, the dose required to treat the arthritis versus the dose that poisons the patient, is incredibly narrow. The data shows that historically, about one-third of all patients who started a regimen of gold therapy had to abandon it because the side effects were just intolerable. If a patient was on gold salts, doctors had to constantly, obsessively monitor their renal function and run continuous blood counts to ensure the medicine wasn't shutting down their organs.
Which is exactly why, if you go to a rheumatologist today, they probably won't prescribe you gold. Modern medicine has largely moved on. We now have biologically based, gold-free molecules called biologics, like Humira, Enbrel, or Remicade. These are engineered proteins that target the exact, specific inflammatory pathways of rheumatoid arthritis much more effectively, and generally with a more manageable side effect profile. Gold salts were a crucial, pioneering stepping stone in the history of rheumatology, offering hope when there was none, but their systemic toxicity limits their utility today.
However, there is one medical field where pure metallic gold has been a superstar for millennia and continues to be highly relevant: dentistry. Because pure gold is so malleable, and crucially because it absolutely does not corrode or tarnish in the wet, highly acidic, hostile environment of the human mouth, it has been used for crowns, inlays, and fillings since antiquity. It conforms perfectly to the shape of a cavity, sealing it tightly against bacteria.
But as we established earlier, pure 24-karat gold is incredibly soft. If a dentist made a molar out of pure gold, you would literally chew it flat over time. So dental gold is almost always alloyed. They mix it with silver, platinum, or copper to give it the necessary structural hardness to withstand the biting force of the human jaw. Though the research notes that dentists used to use something called the gold foil technique. They would take tiny, pure, cohesive rolls of gold foil and literally pressure weld them directly into a cavity, compacting it layer by layer. It creates an incredible seal, but it requires intense, specialized skill from the dentist and is pretty rare to find these days. But let's talk about the lived experience of having gold in your mouth. If you have a gold filling, you might have experienced a very specific, sharp phenomenon. Have you ever taken a sip of a freezing cold drink with a gold filling and felt an intense, shooting zing of pain straight down into the tooth?
That intense sensation is a direct consequence of gold's physical properties. Gold is an exceptional thermal conductor. Natural tooth enamel is an insulator. It protects the living nerve tissue inside the tooth from rapid temperature changes. But when a dentist replaces part of that enamel with gold, you introduce a thermal superhighway. The sudden, drastic temperature drop of an ice-cold drink is transferred through the gold directly into the sensitive pulp of the vital tooth almost instantaneously, causing that sharp shock of pain.
But there's another, even more bizarre, almost sci-fi phenomenon associated with dental gold that the sources highlight. It's called oral galvanism. It is basically the experience of having a literal functioning battery inside your mouth.
It sounds absurd, but the electrochemistry is entirely real. A battery functions by having two dissimilar metals connected by an electrolyte solution, allowing ions to flow and create an electrical current. In the human mouth, saliva acts as an excellent salty electrolyte pool.
So, imagine you have a gold alloy crown on a tooth on the top of your jaw. And let's say a few years later you get a cavity on the bottom jaw, and the dentist uses a cheaper silver mercury amalgam filling. Now you have two dissimilar metals. If you bite down and those two metals physically touch, or even if they're just in close proximity, connected by your saliva, you complete an electrochemical circuit. You create galvanism.
And the patient will absolutely feel it. This microcurrent can cause unexpected, sharp shocks of electrical pain. It can lead to localized inflammation of the mucosal tissue surrounding the teeth, and very commonly, it causes a persistent, highly unpleasant metallic taste disturbance in the mouth as metal ions literally migrate through the saliva. Your own jaw becomes the battery housing.
It's wild. To avoid turning their patients into walking batteries, modern dentists are increasingly moving toward advanced composite resins and durable porcelains. These materials mimic the natural color of teeth, they act as thermal insulators so you don't get the cold shock, and they are electrically neutral, completely eliminating the risk of galvanic shock.
The transition from using gold in dentistry toward modern synthetic composites actually mirrors another massive global shift in how humanity utilizes this element. For thousands of years, if you mined gold, its primary destination was obvious. It was turned into jewelry, minted into coinage, or used for opulent decoration. It was meant to be seen. But if we pivot our attention to the modern era, specifically the technology inside our pockets, we see a radical, almost invisible transformation in demand. Today, the technology sector drives roughly 80% of gold's industrial demand. It has become the invisible, essential backbone of our entire digital infrastructure.
Here's where the story of gold gets really interesting because it stops being about vanity and starts being about functionality. When you crack open a computer motherboard or a smartphone or a high-end digital camera or even the control modules in a modern car, you see gold plating everywhere. It's on the circuit boards, it's on the connection pins, it's inside the microchips. And the immediate obvious question is, why gold? Why are profit-driven tech companies spending billions of dollars on a precious metal when copper exists? Copper is actually a slightly better electrical conductor than gold, and it is vastly exponentially cheaper. So why use gold?
It comes right back to the chemical quirks we discussed earlier: nobility and malleability. Copper is a fantastic conductor, but it oxidizes. It reacts with the oxygen and moisture in the air and tarnishes, forming a layer of copper oxide. If you have a mass electrical wire in your wall, a little surface oxidation doesn't matter much. But if you are dealing with a microscopic copper connection inside a sensitive memory chip and it oxidizes, the electrical resistance of that connection increases, the signal degrades, the data gets corrupted, and the entire multi-thousand-dollar device fails.
So gold is essentially the ultimate insurance policy.
Precisely. Gold, being a noble metal, completely resists corrosion and oxidation. A gold connection will remain perfectly conductive for decades, regardless of humidity or environmental exposure. Furthermore, its extreme ductility, which we noted earlier, means engineers can manipulate it at truly microscopic scales. They can draw gold out into unimaginably thin bonding wires thinner than a human hair that connect the fragile silicon die of a semiconductor to its external packaging. In consumer electronics and critical infrastructure, where long-term reliability and the precise, uninterrupted transmission of data at high speeds are paramount, gold's unique combination of physical and chemical properties makes it virtually irreplaceable. You cannot build a reliable internet without it.
To give you some hard numbers on what that looks like in daily life, the sources break down the precious metal content of an average smartphone. They specifically note that an Apple iPhone uses slightly more precious metals than the industry average, but generally a single smartphone contains about 0.034 grams of gold. It also contains silver, palladium, and traces of platinum. Now, 0.034 grams of gold is physically tiny. It's worth maybe $2 or $3 in scrap value. If you hold a phone, you don't think you're holding a gold mine. It doesn't sound like much.
It doesn't until you scale it up. You have to multiply that fraction of a gram by the billions of smartphones, tablets, laptops, smartwatches, and automotive sensors currently in existence globally. The sheer volume of consumer electronics requires thousands of tons of gold, and this demand is accelerating at an unprecedented rate, largely driven by the current AI revolution.
This is a huge point in the World Gold Council data. The electrification of everything, and specifically the explosion of artificial intelligence, is changing the landscape of industrial demand. Generative AI tools, large language models, they don't run on magic. They require massive, warehouse-sized data centers. They require specialized, incredibly complex processors and high-bandwidth memory chips that run continuously at high temperatures, processing unfathomable data loads. Every single one of those high-performance semiconductor chips relies on gold pathways for reliable performance. We are currently building the physical infrastructure for a completely new era of computing, and that infrastructure is lined with gold. Which brings us to a critical, rapidly mounting global crisis: electronic waste.
The e-waste boom is staggering in its scale. A recent United Nations report highlighted in our materials found that the world generated roughly 62 million tons of electronic waste in the year 2022 alone. And the projections from the World Economic Forum are even more alarming. They project that global society will be tossing out 80 million tons of e-waste annually by the year 2030. That is literal mountains of old cell phones, obsolete hard drives, discarded motherboards, and broken sensors sitting in landfills around the world.
And remember how cosmically rare gold actually is. The sources give a fantastic, mind-bending visualization that really puts this waste into perspective. If you gathered every single ounce of gold ever mined in all of human history, every pharaoh's mask, every pirate doubloon, every wedding ring, and every circuit board, and you melted it all down into one solid cube, that cube would measure just 21.7 meters on each side. That's about 71 feet. That's it. All the gold in human history would easily fit inside the diamond of a baseball field. And yet, we are currently throwing a massive, significant percentage of this finite, cosmically rare material into the garbage every single year because it's trapped in old tech.
This realization, the sheer inefficiency of it, is driving a massive surge in an industry known as urban mining. Instead of spending billions of dollars to dig 4-kilometer deep, environmentally destructive mine shafts into the Earth's crust, like the massive gold mines in South Africa companies, are realizing that our own cities are the richest, most concentrated gold mines on the planet. Globally, it is estimated that there is between $55 billion and $60 billion worth of precious metals trapped inside abandoned circuit boards sitting in desk drawers and landfills. The density of gold in a ton of discarded smartphones is significantly, mathematically higher than the density of gold in a ton of high-grade gold or pulled from a traditional subterranean mine.
It's an absolute gold rush, but instead of panning in rivers, they're sorting through recycling plants. Business Insider reported that some small, specialized startups engaged in urban mining are bringing in up to $85,000 a day just by efficiently recycling these electronic circuit boards. Even ancient, traditional institutions are pivoting their entire business models to get in on this. Look at the Royal Mint in Britain. They have been striking coins for the monarchy for over 1,000 years. But as society uses physical cash less and less, the Royal Mint recently opened a massive precious metal recovery plant. They are actively shifting away from making coins to recycling e-waste, and they are taking the recovered gold from old laptops and turning it into high-end luxury jewelry.
However, historically, recycling e-waste has been a remarkably dirty, dangerous, and environmentally toxic business. Because the gold is plated so thinly onto complex plastic and fiberglass boards, recyclers often relied on the exact same highly toxic cyanide solutions used in traditional mining to chemically leach the gold out of the electronics. Or they would just burn the boards, releasing toxic fumes. That environmental hazard has been the main bottleneck preventing urban mining from scaling up globally.
But there is massive innovation happening right now. The Garfield refining source in our materials highlights incredible advancements in safe, clean recovery. A company called eWorks, in a joint collaboration with researchers at Cornell University, has developed a revolutionary new approach to completely replace toxic cyanide in the recycling process. They engineered a specific environmentally benign organic compound.
And this compound functions essentially like a chemical sponge. When introduced to shredded electronic scrap, it safely and efficiently absorbs the gold ions out of the complex mixture of other metals and plastics without the devastating environmental impact of cyanide leaching. As this clean extraction technology scales up and becomes economically viable, industry analysts project we could see up to 40% of the global demand for rare metals met entirely through clean recycling of old technology by the year 2050.
So we've traced the journey of gold from the explosive deaths of neutron stars to the ancient acid tests to the medical injections, right up to the circuit boards of our AI servers. Now, we have to talk about the underlying force that drives all of this intense mining, refining, and recycling in the first place: human economics. Let's look at the financial weight of gold, specifically using some very fresh data from a 2026 investment research report from UBS and historical data from the American Institute for Economic Research.
To understand the sheer economic gravity of gold today, let's look at the current demand figures. According to the World Gold Council and updated data from UBS, actual total global gold demand in 2025 exceeded 5,000 metric tons for the first time in recorded history. And where does all that gold flow? Historically and currently, the largest single sector is still jewelry, which accounts for roughly 50% of total global demand. This sector is heavily dominated by markets in India and China, where purer, higher-carat gold jewelry is deeply embedded in cultural traditions, weddings, and acts as a primary vehicle for familial wealth preservation. Another 10% goes to the technology and industrial sectors we just thoroughly explored. The remaining 40%, a massive and growing sector, is driven entirely by investment demand. This includes retail buyers hoarding physical bars and coins, institutional investors buying gold-backed ETFs, and crucially, central banks managing national reserves.
And it is that voracious investment demand that is driving prices to absolute, unprecedented record highs. The UBS report is incredibly bullish on the future of the metal. They note that the gold rush has continued with immense strength into early 2026. Gold prices recently surged 28% to hit a new all-time high of $5,600 an ounce. And UBS has significantly raised their future forecasts. They are actively projecting gold to hit $6,200 an ounce by the third quarter of 2026. They even outline an upside scenario driven by major global instability that could push the price as high as $7,200 an ounce. And what's fueling this massive run-up? The sources point to a perfect storm. Escalating geopolitical tensions causing investors to seek safe havens, deep institutional concerns over U.S. domestic policy and massive fiscal stress, a weakening of the U.S. dollar's purchasing power, and perhaps most importantly, massive sustained buying by global central banks. For example, the Polish central bank just dramatically increased its official gold holding target to 700 metric tons. National institutions are actively hoarding this metal.
If we connect this modern hoarding behavior to the bigger picture, this aggressive accumulation by central banks is essentially a modern echo of a monetary system that strictly governed global finance for centuries. To truly understand the psychological and economic hold gold has over central banks today, we must examine the history of the gold standard. The American Institute for Economic Research provides a deep, rigorous, and objective look at how this monetary system functioned. Under a true classical gold standard, a nation strictly defines a unit of its paper currency as representing a specific fixed weight of physical gold and legally promises to redeem that paper money for the exact amount of metal upon demand by the public. The classical gold standard era, which was formally established by Great Britain in 1821 and subsequently adopted by almost all major industrial nations by the 1870s, created a globally integrated system of fixed exchange rates.
Now, we need to be incredibly objective as we unpack this because debates over the gold standard versus modern fiat currency can get intensely ideological and political. We are just here to impartially report what the economic historians and the provided sources lay out regarding the mechanical pros and cons of the system. The underlying mechanism that made the classical gold standard function automatically across borders was first described by the brilliant 19th century philosopher and economist David Hume. It is known as the price-specie flow mechanism. It was essentially an automatic, self-correcting regulator for global trade. Let's walk through a hypothetical to see how it worked. Say a country was importing way more goods than it was exporting, it's running a massive trade deficit. Under the gold standard, it had to literally pay for those extra imported goods by shipping physical gold bullion out of the country to its trading partners.
Correct. And this is where Hume's mechanism kicks in. When that physical gold left the country to pay for the imports, the domestic money supply within that country automatically and immediately contracted because the total amount of paper money was legally tied to the total amount of gold in the vaults. With less money circulating in the domestic economy, but the same amount of goods, the general price level of domestic goods and local wages naturally fell. Deflation set in. This domestic deflation made the country's exported goods much cheaper and more attractive on the global market, while simultaneously making foreign imported goods much more expensive for its citizens. This naturally mechanically reversed the trade imbalance, causing gold to eventually flow back into the country until a global equilibrium was restored.
The advocates of the gold standard point to this exact automatic discipline as its absolute greatest advantage. They argue it enforced strict price stability over the long term, preventing runaway inflation. It prevented nations from engaging in competitive currency devaluations to artificially boost exports. And perhaps most importantly to its defenders, it severely physically restricted governments from overspending and running massive deficits because they literally couldn't just print new money to fund their projects without first acquiring the physical gold reserves to back it up. It fostered an environment of highly predictable international trade and steady capital accumulation.
However, the critics of the gold standard argue that those exact same features, the rigid, unyielding discipline and the strict constraint on the money supply, are actually massive, dangerous liabilities, especially during times of crisis. The sources outline that because the total money supply is inextricably chained to the slow, physical, geological process of mining gold out of the ground, economies operating under the standard often faced chronic deflationary tendencies when economic growth outpaced the discovery of new gold. But more crucially, it left governments and central banks with virtually zero flexibility to respond to acute financial panics or sudden recessions. If a severe banking crisis hit, a central bank couldn't easily expand credit or lower interest rates to inject desperately needed liquidity into the system, because doing so risked creating a panic where citizens would demand all their paper money be converted to gold, causing a run on the nation's finite gold reserves and bankrupting the state.
So, if a crisis hits, the system essentially forces the economy to endure a painful recession to reset prices, rather than allowing the government to cushion the blow. And this rigid inflexibility was brutally, catastrophically exposed during the shocks of the 20th century. The classical integrated gold standard entirely collapsed with the outbreak of World War I in 1914. Nations needed to finance massive, unprecedented military spending, and they couldn't do it with just the gold they had, so they unilaterally suspended convertibility, allowing them to print unbacked fiat money to fund the war effort. Then, during the interwar period of the 1920s, several major nations desperately tried to resurrect the gold standard to regain stability, but the attempts were chaotic and uncoordinated.
A prime example cited in the text is Britain's attempt. In 1925, Britain stubbornly returned to the gold standard at its exact pre-war parity rate. But the economic reality had changed. This political decision severely overvalued the British pound against other currencies. As a direct result, British exports became uncompetitive globally, triggering punishing widespread domestic deflation and massive unemployment. Many prominent economic historians point to this poorly managed, ideologically driven return to gold as a major exacerbating factor in the severity and depth of the Great Depression. The inflexible system simply shattered under the immense, unprecedented economic strain of the 1930s. Britain was forced to abandon gold again in 1931 to stop the hemorrhaging of its reserves, and the United States followed suit in 1933. Making it illegal for citizens to hoard gold coins so the government could expand the domestic money supply.
Then, after the devastation of World War II, the global powers met and tried a modified, compromise version known as the Bretton Woods system, established in 1944. Instead of every currency being tied to gold, global currencies were pegged to the US dollar, and the US dollar alone was rigidly pegged directly to gold at a fixed rate of $35 an ounce. This system worked relatively well for a couple of decades of post-war rebuilding. But as global trade massively expanded, and specifically as the U.S. government spent enormous sums of money on the Vietnam War and sweeping domestic social programs in the 1960s, the supply of paper dollars circulating globally far outpaced the actual physical gold the U.S. Treasury held in reserve. Global confidence cracked. Foreign nations started aggressively demanding their gold in exchange for their dollars. And finally, in August 1971, facing a complete run on Fort Knox, President Richard Nixon unilaterally suspended the dollar's convertibility into gold, an event known as the Nixon shock. This decisively ended the gold standard entirely and ushered in the modern era of floating fiat currencies that we live in today.
Which brings us full circle to the $7,200 forecast for 2026. So what does this all mean for today's geopolitical market? Even though our paper money is no longer legally backed by a single ounce of gold, the metal's ancient legacy as the ultimate, unyielding store of value remains deeply, perhaps permanently, embedded in the global financial psyche. When modern fiat systems experience high inflation, when debt levels appear unsustainable, or when geopolitical instability threatens the fragile global order, retail investors and central banks alike instinctively, reflexively retreat to the physical safety of gold. It has transitioned from being the literal mechanical foundation of currency to serving as the ultimate macroeconomic hedge, a tangible, indestructible, universally recognized asset in an increasingly digitized, abstract, and uncertain world.
It is an absolutely incredible, sweeping journey. From two ultra-dense, dead neutron stars violently colliding millions of light years away and sending heavy, newly forged elements across the cold, vast void of space, to meteorites crashing into the early cooling Earth and depositing those precious metals onto the crust, to ancient alchemists using royal water to test its purity, to the pain of a galvanic battery in our teeth, the microscopic bonding wires running our massive AI servers, and the deep, highly secure vaults of global central banks trying to hedge against the inflation of fiat currency. Gold intimately connects the extreme cosmos to our wallets in a way that literally nothing else does. We've covered the astrophysics, the quantum chemistry, the biology, the tech revolution, and the macroeconomic history. It is a brilliant, shining story.
And yet, there's one final, truly mind-bending fact buried deep in the biological source notes that points to a future of gold that is entirely, unexpectedly biological. We talked extensively about how toxic the chemical recycling of e-waste can be, and how companies are currently using engineered organic sponges to extract gold. But what if the ultimate future of gold mining isn't about digging deep into the dirt with heavy machinery or even using chemical vats on shredded circuit boards? What if the future of mining relies on microbes? Deep in the medical and biological research materials is the discovery of a highly specific, rod-shaped bacteria called Cupriovidis metallodorans.
Wait, a bacteria?
Yes. This microscopic organism thrives in extreme environments that are heavily contaminated with highly toxic heavy metals. And it has evolved an unbelievable, almost magical survival mechanism. It can actually ingest highly toxic dissolved gold compounds, the very same ionized gold salts that are severely poisonous to humans and almost all other life, and it metabolizes them. It processes these toxic dissolved ions internally, and to protect itself, it essentially excretes solid, elemental metallic gold. It actively converts a deadly chemical poison into pure, non-toxic gold nanoparticles without harming itself. It is literal biological alchemy happening on a microscopic scale. So as we look to the looming future of our 80 million ton mountains of electronic waste, imagine a world where we don't mine gold with massive diesel excavators or highly toxic cyanide solutions, but where we use giant, sustainable vats of engineered bacteria to literally grow pure gold directly out of our electronic garbage.
Biological alchemy to grow solid gold from toxic trash. That is absolutely incredible and the perfect provocative thought to leave you pondering today. Thank you so much for joining us on this extensive deep dive into the extraordinary source material behind Element 79. We hope we've given you a totally new, profound perspective on that ring on your finger or the complex circuitry in the phone in your hand. Keep looking closely at the ordinary things around you and keep questioning the incredible, intricate world we live in. We'll catch you on the next deep dive.